and welcome back to chapter 5. Today we're going to go over 5.3, which is solving trigonometric equations. So very exciting. So what are our objectives for this section? We're going to use algebra to solve trig equations. We're going to solve trig equations of quadratic type. And we're going to solve trig equations with multiple angles, and then finally we're going to discuss inverse trig functions. Now, this is with the idea that you guys have looked at the inverse trig function handouts that I posted before this video, so hopefully you guys had a good glance at those graphs, and so that you kind of come in aware of what the graphs look like, the trig functions. Okay, so how do we solve a trigonometric equation? So what we do is we do similar how we normally use algebra, like factoring, like terms, all that. Now, what's our goal? Our goal is to have the trig function on the left side of the equation and some number on the right. So let's say, for instance, we want to solve 2 sine of x is equal to 1. Okay, if we divide by 2, we get sine of x is equal to 1/2. Now, when you see the statement sine of x is equal to 1/2, what is it asking? It's basically asking us, okay, what are the values of x, or at what angle does sine of x equal 1/2? Okay, so we can think of the solution, we can come to the solution in various ways. So let's first, this is my favorite one actually, or one of, well, I don't know, I like both of them. But for this one, notice this, okay? So here is our sine of x graph, okay? So this is for, you see the entire period, 2 pi here, and then you have 2 pi here, y equals sine of x, 0 to 2 pi, but it's periodic, so it keeps going over and over again. And if you graph the line y equals 1/2, okay, the values of x where sine of x equals 1/2 are your answers. Those are your solutions, okay? It's very similar to zeros, but do you see here, so at x equals pi over 6, the value of sine of x is 1/2. At x equals 5 pi over 6, the value of sine of x, so in other words, the value of 5 pi over 6, sine of 5 pi over 6 is 1/2, okay? And then you can see that with the red line intersecting the graph. And so then you may ask yourself, wait a second, it keeps repeating. Well, yeah, because the function is periodic. It's going to keep, just like how it crosses the x-axis multiple times, it's going to cross the value 1/2 multiple times. In fact, it does so twice each period. Okay, so how do we, so you see it in the interval 0 to pi, it intersects 1/2 at pi over 6 and 5 pi over 6, okay? So what does that mean? So because it's periodic, we can say that there's infinitely many other solutions, okay? And the way that we do that, because of the period being 2 pi for a sine, you would just write that x is equal to pi over 6 plus 2n pi or 2k pi, or some people write 2 pi k. It really doesn't matter. And then you would also write x is equal to 5 pi over 6 plus 2 pi k. This 2 pi k, or this 2n pi rather, it basically accounts for the repeatedness, okay? So all you really need to know is how to find it within one period, and then you would just attach the 2n pi to the answer, okay? So this is the proper way of writing it, the general solution, so that you cover all your bases, okay? Here's another way to consider the fact that sine of x equals to 1/2 has infinitely many solutions. Okay, so basically, if you look at the unit circle, that's another way to look at this. Where does y equals 1/2, right? At the unit circle, it equals 1/2 at pi over 6 and at 5 pi over 6. Now, all the angles that are coterminal with these two angles are solutions. So, of course, it would be pi over 6 plus 2 pi, pi over 6 plus 4 pi, pi over 6 plus 6 pi, you get it. And then 5 pi over 6 plus 2 pi, boom, one round, plus 4 pi plus 6 pi, and so on. So that's why we would write the solution pi over 6 plus 2n pi, or 5 pi over 6 plus 2n pi, okay? Now let's do another one. let's say we have here solve sine of x plus square root of 2 is equal to negative sine of x. So what we need to do is to get the sine of x's together on one side of the equation. So of course what we do algebra, right? We would add sine of x to both sides, right? And we would subtract root 2 from each side to get the sines of x here on the left side of the equation and the root 2, which will then become negative, on the right-hand side of the equation, okay? So then when we combine like terms, we get 2 sine of x is equal to negative square root of 2, right? So negative root 2. So then we solve for sine of x, we get negative root 2 over 2, okay? So because sine of x has a period of 2 pi, we need to find all the solutions in this interval, okay? So if you remember that table that we went over a few sections ago, you should know by now that the solutions, sine of x is equal to negative root 2 over 2 at 5 pi over 4, so quadrant 3, and 7 pi over 4, which is quadrant 4. Okay, and then finally to account for all the coterminal angles, all the repeated angles, we would just add 2n pi to it. So your solution would be x is equal to 5 pi over 4 plus 2n pi, and then x is equal to 7 pi over 4 plus 2n pi. Okay, here's another example, extracting square roots. Ooh, fancy. So how do we solve this tangent squared of x, 3 tangent squared of x minus 1 is equal to 0? So first of all, we want to isolate tangent, yeah? So we would add 1 to both sides, and then we divide by 3, so we get tangent squared is equal to 1/3. How do we solve for the tangent? We take the square root of both sides. That's what your textbook says, extracting square roots. It's basically taking the square root of both sides. You get tangent of x on the left-hand side of the equation, and on the right-hand side, remember you get plus or minus 1 over root 3, right? Because square root of 1 is just 1 today, and square root of 3 is just root 3. And then when we rationalize the denominator, it's plus or minus root 3 over 3. Now, tangent of x, and this is why I asked you guys to look at the graphs, because I want you guys to know each trig function has a certain period, right? It's either 2 pi or pi. That's how long it goes until it starts repeating again, okay? And they're cofunctions as well. So tangent of x has a period of pi, okay? So we need to find all the solutions from 0 to pi. So where does tangent of x equal root 3 over 3 or negative root 3 over 3 in the interval 0 pi? It equals that at pi over 6 and 5 pi over 6. Now because tangent of x has a period of pi, we don't add 2n pi, we just add n pi to each solution to get the general form, okay? So then you would get your solution to this would be x is equal to pi over 6 plus n pi, and x equals 5 pi over 6 plus n pi, where n is an integer. Okay, let's do another one, factoring. We have here cotangent of x, cosine squared of x, is equal to 2 cotangent of x. So let's first, how do we solve this problem? It might be a little intimidating when you first look at it, but we do how we've always done, right? We set them equal to 0, we factor, right? And we're going to use zero product property. So that's kind of like the way to attack this problem. So we have the original equation, and then we set it equal to 0 by subtracting both sides, subtracting 2 cotangent x from both sides. So that will leave you with cotangent x cosine squared x minus 2 cotangent x is equal to 0. So then we factor, right? What's the GCF in this situation on the left-hand side? It's cotangent x, yeah? So let's factor it out. What are we left with? We're left with cotangent x on the outside of the parenthesis. On the inside, we're left with cosine squared of x minus 2, okay? Let me close parentheses. Now we have 2 factors that equal to 0. And remember a zero product property, we set each factor equal to 0 and then solve, yeah? So if we set cotangent x is equal to 0, okay, where is cotangent equal to 0? Okay, so that's pi over 2. And then where's cotangent squared of x minus 2 is equal to 0? So we have to solve it, yeah? So Adding 2 to both sides, cosine squared of x is equal to 2. Taking the square root, we get cosine x equals plus or minus root 2. Okay, so let's continue. So let's look at this. If I was to graph it, this would be its graph, yeah? It would be like a repeated weird sideways squiggly thing that goes, has asymptote at negative pi and at 0, x equals 0, and then pi again. Okay, so this equation, the equation cotangent x equals 0 has the solution pi over 2 in the interval 0 to pi. Okay, so cosine of x plus or minus root 2 does not have a solution because plus or minus root 2 is outside of the range of the cosine function, right? Because remember cosine function, what's the range of the cosine function? It's plus or minus 1. And root 2 is like 1.4 blah, blah, blah. So it's outside of the range. So you're never going to, it's not going to have a solution. So really the only one of interest right now is this pi over 2, okay? So we're going to do this, it has a period of pi. The general form is going to just be adding n pi to pi over 2. So if you look here, so our final solution will be pi over 2 plus n pi. Okay, so that's our, and if you look at this graph, boom, here it is. Here's a 0 at pi over 2. Okay, let me subtract the pi. Boom, there's another 0 at negative pi over 2. Subtract another pi. There's this 0 at negative 3 pi over 2, right? And here's one at positive 3 pi over 2, and so on. Okay, so let's talk about equations of quadratic type. Okay, so let's say you have a lot of trig functions or equations are of this quadratic type. What does that mean, quadratic type? They follow this kind of format where it's like coefficient, so ax squared plus bx plus c is equal to 0, meaning number times the trig function squared plus a different number times the trig function not squared plus just a number equal to 0. Okay, so it's constant, you know what I mean? So it's like a quadratic. Here's some examples. Let's look at this. Quadratic in sine of x. So it's like 2 sine x squared minus sine x minus 1 is equal to 0. So you can kind of see that they're of quadratic type, because if I was to take this sine of x and I rewrite it in this way, like in parentheses sine x squared, notice that it's 2 times something squared minus the same something minus 1 is equal to 0. So it's a function. It looks like a quadratic function, right? So you can kind of see what I'm talking about here. And then look at this other example, quadratic in secant of x, where you have secant squared x minus 3 secant x minus 2 is equal to 0. Okay, so it's basically secant of x, parentheses squared, minus 3 secant of x minus 2 equal to 0. So how do we solve equations like this? Like, how crazy is this? Well, you'll be happy to know that we already have the tools to solve quadratic functions, okay? We use the same things that we've been doing, which is factoring, and in addition, quadratic formula. So if you cannot factor it, usually it's easier to factor if you can, but if you can't, go ahead and use a quadratic formula and then you'll find your solution, no problem. Okay, so let's continue. Let's do this one. So find all solutions of 2 sine squared of x minus sine x minus 1 is equal to 0 in the interval 0 to 2 pi. Okay, so let's treat this equation as a quadratic in sine of x and factor. So what does that mean? Consider, like, instead of, usually we have like x or t or u or whatever, but sine of x is like our new x, okay? It's kind of like that. If it helps you to rewrite it, you could even write like 2u squared minus u minus 1 and then factor it and then replace it back at the end. Some people do that. I don't, to me it's like the same, but it's up to you, you could do that. So, okay, so here, if I factor this quadratic, I do the 2 parentheses. What's my first factor? It's 2, right? 2 sine squared of x. So I'm going to put 2 sine of x times sine of x, right? And then I want the product of negative 1. So I have positive 1, negative 1. And if I check this, right, I get sine of x minus 2 sine of x. If I do like a little FOIL, like outer and then inner and then outer, and I combine them, I get negative sine of x again. So I'm good, right? This is my proper factoring. And now that I have it in factored form, I just set each factor equal to 0, zero product property again, and then I solve for each one. So I have 2 sine of x plus 1 is equal to 0. That means when is sine of x equal to negative 1/2 on the interval 0 to 2 pi, and it's true at 7 pi over 6 and 11 pi over 6. Okay, and then solving for sine of x here, I add 1 to both sides, and I get sine of x is equal to 1. Well, when is sine of x equal to 1? Well, that's at pi over 2, yeah? Because at pi over 2, on the unit circle, you get the point 0, 1. So sine of x is equal to 1 at that point. So here's your 3 solutions, okay? And that's it for that. Okay, let's see here. Example 5, rewriting with a single trig function. Let's say we want to solve something that has 2 different trig functions. What the heck? How are we going to do that? Well, let's think about this for a second. Okay, so let's say we want to solve 2 sine squared x plus 3 cosine x minus 3 is equal to 0. Okay, so the best way to do these is just to rewrite it so that it's in terms of a single function, a single trig function. So in this case, by now, you should start being familiar with the identities, right? And of course, our favorite identity is sine squared plus cosine squared is equal to 1. Why do we love that identity? Well, that identity allows us to change an equation that had sine into cosine and vice versa. So in this case, we have the identity sine squared of x is equal to 1 minus cosine squared. So I'm going to use substitution, and I'm going to substitute 1 minus cosine squared of x here for sine squared of x. So you see that here on my second line. I don't know if you can see my cursor, but it's 2 times the quantity 1 minus cosine squared x plus 3 cosine x minus 3 is equal to 0, right? Now let's distribute. Okay, we distribute and we combine like terms, right? So 2 minus 3 will be negative 1. Okay, so if we did that and we multiplied both sides by negative 1, we would get 2 cosine squared of x minus 3 cosine x plus 1 is equal to 0. And then let's go ahead and factor, and that factoring is not too bad. 2 cosine x minus 1 and cosine x minus 1 will give me the same quadratic. So now I set each factor equal to 0 and solve. So 2 cosine of x minus 1 is equal to 0 gives me cosine of x is equal to 1/2 because I add both sides by 1 and divide by 2. And where does that equal to, where does cosine x equal 1/2 on the unit circle from 0 to 2 pi? Well, it equals 1/2 at pi over 3 and 5 pi over 3, right? Quadrants 1 and 2. Okay, then we have cosine of x minus 1 is equal to 0, which implies that cosine of x equals 1, right? By adding both sides of the equation, adding 1 to both sides. So where does cosine x equal 1? Well, that's at 0, right? Okay, and then because it has a period of 2 pi, we're talking in general, we add 2 pi n to each one. Okay, so if x is 0, then 0 plus 2n pi, that's one answer. So x is equal to 2n pi. Okay, the other ones were pi over 3 and 5 pi over 3. So x is equal to pi over 3 plus 2n pi, comma, x equals 5 pi over 3 plus 2n pi, where n is an integer, of course. Okay, so let's do another one. So notice the difference between the last example and this one. The last example didn't tell us find all the solutions in the interval. It just said find all the solutions. And because it said find all the solutions, we had to talk about the general type. We had to say, oh, okay, you want all the solutions? Okay, fine. I'm going to add a constant, so that it includes all the coterminal angles, okay? And that's when we add 2n pi or n pi, depending on what you're working with, yeah? But in this case, that's what's really important to read the question carefully, because people don't do that, and then that's how they get things wrong. Okay, so this question says, find all solutions of cosine of x plus 1 equals sine of x in this interval 0 to 2 pi. So this is a type of, this is like a method you can use, because we kind of can think, well, I don't know how to solve this trig function. If I do want to replace sine with cosine, I'm going to get, I don't know enough of the different identities. There are some identities you could use, but in this case, I think right now you only have the access to sine squared plus cosine squared and then some like half angle identity, but then that would be weird because then you'd have a different angle. So that wouldn't work. So then what do we do? So what do I do? What do I do? So one thing you can do is you can actually square both sides, okay? When you square both sides, we get something that we can work with, something that we can now replace using the Pythagorean identity, meaning we can use sine squared plus cosine squared is equal to 1. So that's kind of like our plan of attack here. So let's go ahead and do that. If you square cosine of x plus 1, that's squaring a binomial. Remember, that's a perfect square trinomial comes out of that, yeah? So then we would get here on the second line, we would get on the left-hand side cosine squared of x plus 2 cosine x plus 1. On the right-hand side, we would get sine squared of x. Okay, so now here, look very carefully the second line, okay? Make sure that you realize, wait a minute, now that I've squared both sides, I can totally replace sine squared of x with 1 minus cosine squared, you know? So let's go ahead and do that, okay? So if I do that, what's going to happen? I'm going to move everything over to the left and get 0. So I'm going to subtract 1 from both sides, and I'm going to add cosine squared of x to both sides, and let's see what happens, right? So if I do that, what's going to happen? The cosine squared plus cosine squared will be 2 cosine squared of x. Then you'll have a 2 cosine of x, but these ones will cancel out. So you're finally left with 2 cosine squared x plus 2 cosine of x, equals to 0. So now what do I do? After that, I can factor the GCF. What's my GCF? My GCF is cosine of x. So since my GCF is cosine of x, actually it's 2 cosine of x, I factored that out. What am I left with? I'm left with cosine of x plus 1 in the parenthesis, and now I can go ahead and use zero product property, yeah? So I set each factor equal to 0, and I get 2 cosine of x is equal to 0, and cosine x plus 1 equals 0. And if I solve for cosine x on this first factor, dividing by 2 does nothing. I just get cosine x equal to 0. Okay, fine. Where does cosine x equal to 0? By now we should really start becoming pros, right? In the interval from 0 to 2 pi, cosine of x is equal to 0 at pi over 2 and 3 pi over 2. And if you went over the unit circle like I told you, and you looked at the handouts that I posted, and so this should be making sense to you. This should not be like, what, why, where'd she get this pi over 2? Where'd she get this pi? And if you are thinking that, and if you are asking those questions, please do yourself a favor and go back and look at the extra material that I posted right before this video, okay? Okay, fine. That's enough. So then now I have cosine, on the other factor, I have cosine x plus 1 is equal to 0, and I'm subtracting 1 from both sides. Then I get, where does cosine x equal negative 1? Well, that's easy. On the unit circle, we see very clearly that the cosine of x has a value of negative 1 at pi. Okay? So, yeah. So then after that, you can, because we squared it, what happens is that sometimes we could create what's called an extraneous solution. So you might think like, what does that mean? Well, extraneous solution means that it's a solution that is not actually a solution in the original problem, okay? So let's check, okay? So we're plugging this back into the original equation. So we have pi over 2, 3 pi over 2, and pi. Pi over 2 works out, so that checks, right? You get cosine pi over 2 plus 1 is equal to sine of pi over 2. 1 is equal to 1 today, so correct. At 3 pi over 2, we get cosine 3 pi over 2 plus 1 equals sine of 3 pi over 2, but sine of 3 pi over 2 is negative 1, and cosine 3 pi over 2 is 0, so this does not check. So notice, why did this happen then? This happened because we squared both sides, so if this was squared, it would be true, right? But because that wasn't the original equation, we have to go back and check it and see this solution is extraneous or extra, right? Okay, and then at pi, it works. Cosine pi is negative 1. Negative 1 plus 1 is equal to sine of pi, which is 0 today, and yes, it's true. Okay, so for the final solution, it would be in the interval 0 to 2 pi, the only two solutions are pi over 2 and x is equal to pi. All right, so finally, functions involving multiple angles. So this next example involves trig functions of multiple angles in the forms cosine of KU and tangent of KU. So to solve equations of this kind of form, first we need to solve the equation for KU and then divide by K. So that's all. All right, so let's see, for instance, we have 2 cosine of 3t minus 1 is equal to 0. So of course we would do like how we do. We solve for the trig function. We'd add 1 to both sides, divide by 2. So now basically we're asking, hey, where does cosine of 3t equal 1/2? Okay, so the nice thing about this, so please pay close attention so you do not get lost later. You find it in the same way. You basically ask yourself the same question, okay? Forget that it's a 3t, just think of that as theta or whatever, or alpha, who cares? You ask yourself this, where does cosine equal 1/2 in the interval 0 to 2 pi? Okay, so from 0 to 2 pi, we know that theta, okay, so just theta turns out to be 3t, or you can think of it as the argument or the input of cosine, okay? So cosine of something, cosine function equals what's it called? What was it? 1/2? 1/2 at pi over 3 and 5 pi over 3, right? We know that. But because theta happens to be 3t, we would write it this way. We would write, okay, 3t is equal to pi over 3 plus 2n pi, and 3t is equal to 5 pi over 3 plus 2n pi, right? This is what we would normally do if the 3t was an x, right? So we continue that step. That hasn't changed. The only thing that changed or that will change is the final step, which is dividing everything by 3, okay? Or, you know, multiplying by 1/3, however it makes sense for you, okay? If I divide 3 to everything, right? So here on the left-hand side, I have 3t is equal to pi over 3 plus 2n pi. If I divide this equation by 3, I get t is equal to pi over 9, right? Pi over 3 divided by 3 is the same as pi over 3 times 1/3, which equals pi over 9, plus 2n pi over 3. And similarly, on the other solution, you would get t is equal to 5 pi over 9 plus 2n pi over 3, where n is an integer. Okay, one more. How about this one? 3 tangent x over 2 plus 3 is equal to 0. So what we would do, we would isolate the trig function, yeah? So subtract 3, divide by 3, we get tangent of something, x over 2. If it helps, like I'm saying, just think of it like tangent of theta of blah, like who cares? Tangent of x over 2 is equal to -1. Where does the tangent function equal -1 in the interval 0 to pi? Why is it 0 to pi, not 0 to 2 pi? If you answered, hey, the period of tangent is only pi, you got it, and give yourself a high five. Okay, so where does tangent equal -1 on the interval 0 to pi? We know that it equals, the only place that it equals -1, I mean, is 3 pi over 4, okay? So from 0 to pi, tangent of 3 pi over 4 is equal to -1, okay? So what does that mean? That means we let the input, which is x over 2, equal 3 pi over 4 plus n pi, because tangent has a period of just pi. Okay, so remember this n pi just is basically saying, hey, consider all the coterminal angles, okay, because they didn't tell us to solve over an interval, they just said solve equals 0. So now the last thing we need to do is multiply everything by 2, okay, and then you get x is equal to 3 pi over 2 plus 2n pi. Okay, and finally, we're going to talk about a little bit about inverse functions. Okay, so let's say you have here inverse functions, this really cool equation, secant squared of x minus 2 tangent of x is equal to 4, okay? And then we solve this here, we replace secant squared of x with 1 plus tangent squared of x, which is a Pythagorean identity. right? By now we should start becoming a little bit more familiar with that. So now we have, when we combine like terms, we get tangent squared x minus 2 tangent x minus 3 is equal to 0. And then if we factor this, we get tangent of x minus 3 times the quantity tangent x plus 1. If we set each factor equal to 0, we get two solutions in the interval negative pi over 2 to pi over 2, right? So remember the range of the inverse tangent function is negative pi over 2 to pi over 2. Okay, so what was I going to say? So basically, how do we solve this? We're basically saying if tangent of x is equal to 3, by definition, the inverse tangent of 3 is equal to x. And similarly, the inverse tangent of negative 1 will equal x. Okay, so basically we're saying, okay, if the angle, so if tangent of x is equal to 3, the inverse tangent is equal to, of 3 is equal to the angle. That's because that's how inverse functions work, right? The input becomes the output and so on. But let me show you in the calculator how easy it is, okay? So here we go. Okay, so x is equal to, this is arctangent, but it actually, in your calculator, I'll say tangent and little 1 inverse, negative 1. X equals arctangent of 3 plus n pi, and then x is equal to negative pi over 4 plus n pi, where n is an integer. And we can use a calculator to find that, okay? So we would do just second inverse tangent 3, and then n parenthesis and hit enter, and you'll get a value. And then you can just write this out and put plus n pi, okay? Cool. So that's it for 5.3. You have your super fun homework and any questions, and I will see you in class in the next video. Bye.